Welcome to Lesson 1B, HERP Index. We're going to talk about the HERP Index, which is a way to compare risks between, say, one chemical and another. First, let's define what HERP is. We'll call it the HERP Index. It's an index for measuring and comparing the cancer risk of being exposed to chemicals. In other words, how likely is a certain chemical to cause cancer? The acronym stands for human+exposure+rodent+potency. The way it works is we use mice or rats, rodents, rather than humans. I think you can see obviously why. You don't want to test humans till they get cancer and keep giving them more and more chemicals. But we use rats and mice. You feed them or you make them breathe or you expose their skin to some chemical and you keep giving them more and more of the chemical until they start getting cancer. So we define the HERP index as the human dose in milligrams per kilogram per day. That's the units over a lifetime. So we're going to be comparing a human eating a certain chemical over a whole lifetime per day, or somehow exposed to that chemical, breathing, eating, compared to the rodent milligram per kilogram per day over a lifetime. And this is the rodent TD50, which we define here. That's a potency, which is defined as the daily dose rate in milligram of the chemical per kilogram of body mass over a lifetime, for which 50% of the rodents develop cancer. So this 50% is critical here. So be careful of the factor of 2. So if your risk determined by this HERP index is, say, 6%, your risk of getting cancer is only 3%. There's a factor of 2 there. So a HERP of 100% means that you have a 50% likelihood of getting cancer. And getting cancer is not necessarily dying from cancer. They test these mice and rats and then they check whether they have cancer near the end of their life. So they go for their whole life every day being exposed to these chemicals. This HERP index assumes that rodents scale up to humans. And for some chemicals, this may be a pretty good assumption. For other chemicals, it's not, because we don't have exactly the same physiology. We're not rodents, we're humans. So our bodies act differently to different chemicals. In fact, not even mice and rats scale up. So if you do the same kind of HERP thing with a mouse and a rat, and the rat weighs a lot more, sometimes you're off by an order of magnitude into what harms the rat and what harms the mice. So we got to take all these with kind of a grain of salt.
Then, are these data even useful?
The HERP is useful for comparisons. We can compare carcinogen A to carcinogen B, which one has the greater risk. And I'll do some examples. You'll see how this works. The important thing to remember is a larger HERP means a greater risk. Again, that's the risk of getting cancer. Let's move on to an example. How do you calculate these HERP indices? Suppose your charge is to create a new HERP index. A previously unknown chemical is thought to cause cancer, so mice are tested in the lab. We need to determine their HERP index to add it to the existing HERP tables. So here's some numbers. The average mass of the mice used in the test is 25 grams. The mass of the average human, this is a standard human male, we'll see this number over and over again, 70 kilograms. And when the mice eat 2.0 milligrams of this chemical, again, this has to be every day of their lives, 50% of those mice develop cancer. So let's calculate the HERP index. We need some definitions here. HSS we're going to call the HERP serving size, and I'll define all of these below. Assume that a standard human male is going to eat or breathe, however this thing is done, 4.5 milligrams per day every day of his life. This is the definition of HERP. It's a percentage, so it's the human dose, milligram per kilogram per day over a lifetime, over the rodent TD50, where TD50 is the daily dose rate, which causes 50% of the rodents to develop cancer. I already mentioned HSS is the serving size used in the test for the HERP index table. So this is what you're actually using in the table. ESS could be different from HSS, is the exposed serving size. When we do problems, for example, HSS might be 1 cup of coffee, but we're going to say a person eats 2 cups of coffee, so we'd have N equal 2, but even that cup could be different. You could be talking about an 8-ounce cup versus a 10-ounce cup, so you got to be careful. The HSS and ESS are not always the same. HERP is what's reported in the table. I already said the N is the number of serving of the exposed serving sizes. So N times ESS will be the dose that's actually eaten by, breathed into, or otherwise exposed to the person every day. These will become more clear as we do some more examples. So first thing I want to do, to calculate HERP, I need to calculate the TD50. So I'm going to use this equation. TD50 is the daily dose rate over a lifetime for which 50% of the rodents develop cancer. Well, we've already showed that up here. That was given. We have their mass, and we have this 2.0 milligrams of exposure is how much is needed for 50% of the mice to get cancer. So TD50 will be 2.0 milligrams of the chemical over 0.025 kilograms. I converted 25 grams to kilograms because we need it in milligrams per kilograms. That turns out to be 80 milligrams per kilogram. So that's the daily dose rate per mass of the mouse that causes 50% of them to give cancer. For a man with the same risk, he would need to eat, let's take 2.0 milligram per 0.025 kilogram times the mass of the man, which is kilograms. So we assume this is proportional, and this turns out to be 5,600 milligrams per day. So I didn't ask you to calculate that, but this is what it means, that if an average man of 70 kilograms ate or breathed or otherwise was exposed to 5,600 milligrams per day of this same chemical, we would expect 50% of those type of men to get cancer. You can verify, for this case, the HERP index would equal 5,600 milligram per 70 kilogram divided by, so I'm using this equation, the human dose over the rodent dose, which is our 2.0 milligram per 0.025 kilogram times 100%, and you get 100%. So that's what we expected, because that's what I calculated. So in other words, a HERP index of 100% means there's a 50% chance of the person getting cancer. But the person is actually not eating 5,600 milligrams per day, but only 4.5. So the actual HERP, so this would be at the HSS 4.5 milligrams, which we're using in the HERP table. The HERP value would be 4.5 milligrams per 70 kilograms. I'm just doing the same equation except for 4.5 instead of 5,600 over 2.0 milligram per 0.025 kilogram times 100%, and that comes out to be 0.08%. And I'm only giving this answer to one digit. So this is what we would add to the HERP table. So the HERP table, the data are listed as a percentage. So I want to show you the HERP table on the websites. Here's the HERP table. The HERP percentage is given on the left, and it tells you what the chemicals are, etc. So that's how we can look up the HERP values. Here's another example problem then. This will be similar to what you'll be doing for homework and for the quiz. So we're using the HERP index for comparison of carcinogens. We're given that bacon, it has some carcinogens, and diet soda has some carcinogens, namely saccharin for this type of diet soda. So using HERP data, we're going to calculate how many 30-gram servings of bacon per day, every day of your life, you would need to eat to have the same cancer risk as drinking the average amount of diet cola with saccharin every day of your life. So you're going to drink 1 can of soda a day as the serving size. So here's the useful equation, which is on the equation sheet, by the way, and all these variables are defined above. I want to discuss this table, how to use it. These are arranged in more risk the higher it is on the table. So you can see it starts at 140, 17, 12, etc. Keeps decreasing as you go down. It's based on a HSS, like if you're looking at celery here, 14 grams of celery, this would be the HSS that HERP table is based upon. Now you may be eating a 20-gram stalk of celery, not a 14 grams, so that would be your ESS. So you got to be careful the HSS is not the same as the exposed level. This is just what the table is based on. And it's usually milligrams or grams, like here it's milligrams, here it's grams. So you got to be careful of units also. Over on the right is the potency, TD50 in milligram per kilogram per day. And notice that they have rats and mice. They use the smaller one, which in this case is for rats. Notice there's a big difference between rats and mice. And when it's in parentheses, that means they did not use this value. They used the rat value. It's the smallest one, which is most conservative. That's how they came up with this number. All right. So in our problem, we have two types of things we're eating: diet soda with saccharin and bacon. Now, I would recommend you go to the website and do a search for saccharin, and you would find one entry for saccharin, 0.005, due to the chemical saccharin. So they fed poor little mice, or these are rats, a lot of saccharin to get to this value. For bacon, you do a search for the word bacon, and you're going to actually find three. If you do a search, you'll find these three entries. We got to add them all up when there's more than one. So there's three different chemicals in bacon that each one of them as an individual chemical can cause cancer. Notice that these are 19-gram servings. This is the HSS for bacon. This would be, the saccharin is just 1 can. You have to read some of the notes to figure that out. 7 milligrams is 1 can of saccharin. The solution is, first let's set up the variables so I know what I'm talking about. We're going to let N be, remember N was the number of servings, so the number of servings of bacon, and these are always per day, and this is going to be our unknown. That's what we want to solve for. By the problem statement, says how many 30-gram servings of bacon. Notice that 30 grams is different from 19 grams, so we got to be careful and put all the variables correctly into this risk equation to do it right. So NB is the number of servings of bacon per day, which is unknown. We'll let NS, B means bacon, S means soda. Number of servings of the soda per day is equal to 1 can. The ESS, exposed serving size of bacon, is 30 grams. That's the serving size that we're looking at, that we're examining, as given in the problem statement. Notice that the HSS is for bacon is 19 grams. So ESSB is 30 grams. ESS, the soda, is also 1 can. That's not immediately obvious from the table. You have to look up some of the notes for that. HSS of the bacon is equal to 19 gram. This is from the HERP table. HSS of the soda is 1 can. So sometimes the ESS and the HSS are different. Sometimes they're the same. But if we write these variables, we can't go wrong. And then we look up the HERP index, or the HERP as a percentage for the bacon. Now I have to add up all three of these. So I have a 0.001, I have a 0.0008, and a 0.007. These are all percentage. So this would be 0.001 plus 0.0008 plus 0.0007% equals 0.0025%. And then the HERP of the soda, there's just one value there, and that's 1 can. All right, now I'm able to calculate the risk. The bacon risk for getting cancer is equal to N times ESS times HERP over HSS. So use this equation here. I'm going to do this for both of the chemicals, both of the substances that we're exposed to here. I'm going to put a subscript B, NB, ESS B, HERP B divided by HSS, the HERP serving size B. And then the soda risk is equal to the same thing except with S subscript. And the key to solving this is we want to equate these two, because what we're asking how many 30-gram servings of bacon would you need to eat to have the same cancer risk as drinking this can of soda every day. So we want to equate these two risks and solve for the unknown. And the unknown, of course, is our NB, which we're trying to solve for. And so we can just make an equation by equating these two and solving for NB is equal to NS times ESSS times HERP-S over HSSS times HSSB over ESSB HERP-B. This is our answer in variable form, which I recommend that you always try to work as far as you can in variables before you plug in the numbers and get NB equal. NS was 1 serving. There's no units with that. ESSS was 1 can. Then the HERP was 0.005% for the soda. That's from up here, 0.005%. That comes directly from the table. Divided by HSSS, which is also 1 can. And then HSS of the bacon is 19 grams. The ESS of the bacon is 30 grams. And then the HERP of the bacon is 0.0025%. And when you plug that all in, you get 1.27. All the units cancel out, the grams, the cans, and the percents. So we just have a ratio, which is a number of servings. It's a non-dimensional number. So I would give my answer as 1.3 servings per day. So these are almost equivalent, about 1 or so servings of bacon to be equivalent risk of cancer of drinking 1 can of soda per day. All right, some comments. One of my pet peeves is significant digits. If any of you had had me for previous courses, you know that. Most books don't treat significant digits carefully, but these HERP values are good to, at most, 2 significant digits. So we'll give our answers generally to 2 significant digits. They're really only about 1. In this particular case, the HERP value for the soda is 0.005%. There's only 1 digit given. But given that there can be such a variation between even rats and mice, there's about a factor of 2 there. You can't be very accurate with this, especially because, like I said before, rats and mice don't always scale up to humans. So we're going to give 2 significant digits for these kind of answers. I also want to comment the actual cancer risk is what? Well, from the HERP table, drink 1 can of soda a day every day of your life was 0.005%. So the actual risk of cancer is half of this. Remember that factor of 2. So the risk of getting cancer is 0.0025% because of that TD50, the 50% value. This all assumes rodents scale up to humans. But as we already said, that is not always the case. So make sure you watch your units and the difference between the HSS and the ESS. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.